I think every time I come, I talk about polynomial threshold functions. OK, thanks. So this is joint work with a bunch of co-authors. It kind of represents some different papers, and some new co-authors are actually going to show up as well halfway through the talk. So that's something to look forward to. OK, did that work? Oh, I pressed this button, yeah. So let me give you a high-level outline of the talk so you can get used to the sound of my voice for 30 seconds. I'll start off with a little introduction, kind of telling you what I'll be talking about. Essentially, the high-level overview is that we have a body of results for linear threshold functions, simpler functions, and we're trying to extend as many of them as we can to polynomial threshold functions. And we succeed in doing this in some cases. I'll spend the bulk of the talk on the main result, which is sketching a proof of an average sensitivity bound for polynomial threshold functions. I'll tell you kind of the high-level picture of how the proof works, hopefully in a convincing way. And I'll spend some time then on applications. So I'll focus on two applications. One is to getting some new learning results, learning threshold of AC0 circuits. So kind of a richer class of circuits than we could handle before. And I'll talk a little bit about connections between the average sensitivity result and noise sensitivity. And as a consequence of having a noise sensitivity bound, we get agnostic learning for low-degree polynomial threshold functions, which is a question some people had been interested in. And I think I should be able to talk a little bit as well about kind of a refinement of the original proof, which gives us what I'm referring to as a regularity lemma for polynomial threshold functions. So that's the high-level structure. And of course, ask lots of questions if you're interested. OK. So let me start off by reminding you just of kind of the d = 1 case, linear threshold functions. Throughout the talk, we'll be focusing on Boolean valued functions. OK, so functions on the Boolean cube that give us just a single bit of output. And let's start with linear threshold functions. Oops. Oh, thanks, Avi. Thanks. Great. So I'm more likely to fall off the stage and make this a talk to remember. Yeah, so in the d = 1 case, a linear threshold function is just exactly what you expect, the sine of some linear form. OK, and geometrically, it's a hyperplane cutting through Rn. Think of these as points of the Boolean cube. Some lie on one side, some lie on the other side. That's what we've got. So these functions are interesting. I feel like I have to give you a little mandatory 30-second spiel. We care about these functions for lots of reasons. They come up all the time in computational learning theory and machine learning. Basically, if we have a provably effective learning algorithm for a class, you can almost guarantee that somehow you're learning linear threshold functions in disguise. So algorithms like perceptron, Winnow, kind of practical algorithms like support vector machines, boosting, they all basically work by learning linear threshold functions in some way. They're obviously interesting in complexity theory. Classes like TC0 are just constant depth circuits of linear threshold functions. And they come up in other fields too. If you think of like a voting scheme with weighted voting, California has, I don't know, 35 electoral votes. Some other state has some other number of electoral votes. Those are like different weights in a linear threshold function. OK, so they're kind of an interesting class of functions. And we know sort of a lot of things about linear threshold functions. I'll take you briefly through a tour of these results. So I guess 40 years ago now, practically, there are bounds were given on the average sensitivity of linear threshold functions, essentially just measuring the number of edges of the Boolean hypercube that a hyperplane can cut. We'll define these notions more clearly in a second. I guess about 5 or 6 years ago, Perez gave a nice proof of the noise sensitivity of linear threshold functions. So if you flip a couple of bits of an input string, how likely is it to cross from one side to the other? And there are applications of having this noise sensitivity bound to agnostic learning. We get computationally efficient agnostic learning algorithms for linear threshold functions as a result of the noise sensitivity bound. More recently, there's been some kind of work on coming up with a body of structural results for linear threshold functions, and there are some kind of algorithmic consequences too. So some work from the last couple of years, we showed that every linear threshold function over the Boolean cube has a low weight approximator. There's some integer weight representation of the linear threshold function. So all the coefficients in the linear form are integers, and those integers don't have to be very large.
It's well known that exactly they have to be large.
Yeah. If you want an exact representation, then over n variables, they actually have to be as large essentially as n factorial. But if you want, say, a 99% accurate linear threshold function, you can get away with linear in n. Actually, square root of n is the largest magnitude of any individual weight. The weights you can approximate with very low weight linear threshold functions. So I guess that's just kind of a result about approximating linear threshold functions. But the ingredients in that result have various applications. So we had this work with Ryan O'Donnell on sort of the Chow parameters problem. So if I give you just the degree 1 Fourier coefficients of a linear threshold function, so constant in degree 1, I tell you the bias of the linear threshold function, and I tell you the correlation of the linear threshold function with each individual variable, there's an efficient algorithm to reconstruct a high accuracy approximation of the linear threshold function. So that's the so-called Chow parameters problem. You can describe it as some kind of learning problem, the so-called restricted focus of attention learning model as well. Some kind of different algorithmic work that plays off of these structural results on linear threshold functions is a property testing algorithm. So the class of linear threshold functions over the Boolean cube, that's a class of functions, and we can test it with poly 1 over epsilon many queries. So you give me any black box function, I'll make poly 1 over epsilon queries. If it is a linear threshold function, I'll say yes with high probability. If it's epsilon far from every linear threshold function, you'll say no with high probability. Okay? And I guess more recently, there's been some work on pseudorandom generators for linear threshold functions, and even follow-up work coming up in this next talk on pseudorandom generators for polynomial threshold functions as well, which is related to what I'll be talking about. Mecca Zuckerman? Yeah. So to boil the slide down, linear threshold functions are very well understood, and kind of the motivation for this talk is we'd like to understand polynomial threshold functions just as well. Okay, we don't, but we're trying to sort of get there. So it looks like I made my font a little bit too light, which is good. We don't have analogs of these results. I won't talk about whatever this was, the Chow parameters, the pseudorandom generators, and so on for polynomial threshold functions, but we make progress on sort of these bullets for polynomial threshold functions. And the bulk of the talk will be spent on the first result, average sensitivity. Okay? Okay, so what's a polynomial threshold function? This is not going to come as a surprise, right? A linear threshold function is the sign of a linear form. A polynomial threshold function is the sign of a polynomial. We'll think throughout this talk that we're dealing with low-degree polynomials. So, d for the whole talk is going to be the degree of the polynomial whose sign we're taking. And think of it as, I don't know, 2, 3, 5, 10. It's like a small constant or a very slowly growing function or something like that. Okay? So, maybe this is kind of a picture to have in your mind. You have a curvy shape, and points on one side are positive, points on the other side are negative. Okay, so we're going to be talking about average sensitivity of polynomial threshold functions. Let's just remember what average sensitivity is for a Boolean function in the first place. It has a lot of names. You may be used to thinking of it or referring to it as total influence, the energy of the Boolean function, the Bonjoff power index, the edge boundary density. There's lots of sort of equivalent ways of saying the same thing. But what is it? You've just got some Boolean function. We say that the sensitivity of the function at a given input, at a fixed input x, is just the number of bit positions, coordinates 1 through n, where if you flip that one coordinate, it makes the function's value change. Right? The number of coordinates at which it's sensitive. So I think I'll use this notation occasionally. If you flip the ith bit of an n-bit string x, it's like this x with a little plus I. The average sensitivity of f, not surprising, is just the expected value, the average, averaged over all 2 to the n inputs, of the sensitivity of f at x. Okay? So it's obviously between 0 and n. If you have a constant function, the average sensitivity is 0. Flipping an edge never changes it. If you have the parity function or its negation, then for any input, flipping any edge out of that input changes it. Okay? So we can also think of average sensitivity, and it'll be convenient to do this for us sometimes as the total influence of all the variables on the Boolean function. So if you have a given variable, variable I, the influence of variable I on your Boolean function is just the probability that flipping the ith bit of a random input changes the value of the function. Okay? So it's kind of like measuring how many edges are there in the ith direction of the Boolean cube where the function changes. The total influence, you're just summing this across all n directions. So it's probably pretty obvious that average sensitivity and total influence are just two ways of talking about the same thing, right? You're measuring the number of bichromatic edges in the cube, and with average sensitivity, you're sort of measuring it on a vertex by vertex basis, adding it all up. And with total influence, you're saying, okay, how many bichromatic edges are there in direction 1, direction 2, direction 3, so on and so forth. But it's the same thing. Sometimes it'll be useful for us, though, to sort of try to get a handle on average sensitivity by thinking coordinate by coordinate. So we should have the second point of view, the total influence in mind as well. Okay, so basically the main topic of this talk is, I guess you could think of it as a geometry question, which is represented by a very poorly drawn figure over here. Say you have a degree d polynomial. So I guess this is like a little degree 2 polynomial. It's a parabola. I'm trying to draw really like, what am I trying to say, a surface in R3 for this little example, but my artistic skills are not that good. So imagine like you're looking straight down the parabola. It's like a tunnel, and you're just seeing the wall of the tunnel with this picture here. Given this polynomial, of course, we have a corresponding polynomial threshold function, the Boolean function, right, where I guess the green points are the positive side, the blue points are on the negative side. So just which side of the parabola you're on, right? We know the average sensitivity, the total influence, or whatever you want to call it, is just the number of bichromatic edges, the number of edges that are blue on one point, green on the other, sliced by the surface. So the question we're interested in is, you give me a degree d polynomial, how many edges can it slice in this sense? Right? How many edges can there be in the Boolean cube where it's positive on one side, negative on the other? So we're just saying, we're asking the question, what is the maximum possible average sensitivity of a degree d polynomial threshold function? Okay? So fortunately, we know the answer. Unfortunately, we can't prove it. But let's go through a couple of sort of small examples to work our way up to the answer. This is about as small as you could reasonably get. It's a three-dimensional example, so n equals 3. And we're interested in degree 1 polynomial surfaces, so just slicing an actual, like, cube of cheese with a knife. What is the best degree 1 surface, the best hyperplane? Well, this is what it is. You should slice it sort of on this funny diagonal, and you can cut, I guess, 6 edges. This corresponds to the majority function, and you can easily convince yourself this is as good as you can do. Let's take it up to the next level. So we'll go to n equals 4. Okay, I've drawn the 4-dimensional hypercube here to the best of my ability. It wasn't pretty when I was drawing this, but here it is. So, and we're going to think about slicing it with a degree 2 surface. So I could put a little ellipsoid. I could put some kind of hyperbola, something like that. What should you do? Well, the best thing you can do is really put sort of an infinitely fat or infinitely elongated, infinitely smushed down hamburger. Right? You can achieve 2 parallel hyperplanes, right, just by some little polynomial like this. The sum of x1 plus x2 plus x3 squared equals 1. So, right, that's a degree 2 polynomial. And you can see we're sort of slicing all these edges, crossing the middle 2 layers of the Boolean cube. And this is the best you can do with a degree 2 surface in 4 dimensions. So far, so good? OK. So, this is embarrassing. 3 dimensions, 4 dimensions. We care about n dimensions. What's going on in n dimensions? Well, for degree 1, we know the answer. That was this result of O'Neill that I mentioned a couple slides ago. Right? He proved that the hyperplane that maximizes the average sensitivity, the hyperplane that cuts the most edges of the Boolean cube, is just any hyperplane sort of slicing the middle of the Boolean cube on a diagonal. So you can think of it as like the majority function or the hyperplane, the sum of the xi's equals 0. Right? So I'll have a couple of pictures like this. This is the all 1's point of the Boolean cube. This is the all minus 1's point. And the polynomial, it's a degree 1 polynomial, obviously. You can write down some little combinatorial expression for the exact number of edges that it slices. This is probably incorrect because n is even or n is odd or something. But it's the average sensitivity is on the order of root n for this guy, right? It's an easy computation. You don't go in an axis-aligned way. Yeah, so an axis-aligned slice. Yeah, everything's fine. You want to actually slice the edges. You don't want to pass through any vertex. So yeah. So I guess I'm thinking of, if you think of the cube as sort of rectilinearly oriented, twist your point of view or twist the cube. So like the all 1's vertex is up here, the all minus 1's vertex is here, and just as you go down, you're sort of this is the layer where the sum of the inputs, half of them are even or half of them are odd. Okay? Okay. So good. We know what's going on in 1 dimension. And it's easy to prove this. It's not a hard result. I guess 15 years ago, Craig Gotsman and Linial gave a conjecture about the degree d case, kind of a bold conjecture. They said, hey, we think we know exactly what the degree d PTF is that slices the maximal number of edges. And it's just the generalized version of this hamburger from a couple of slides ago. Right? They conjectured that the degree d PTF, that maximizes the average sensitivity is a symmetric function that just slices the middle d layers of the hypercube. So it's like a univariate polynomial of degree d. And what you do is you plug in the sum of the xi's, the sum of the inputs. And by having the appropriate univariate polynomial, it'll be positive and 0, negative, positive, negative, positive, negative. So you're slicing the middle d layers of the Boolean hypercube. This feels like a good thing to do. There's a lot of edges there, right? In particular, you can get d times square root of n. Each of these d middle layers, as long as d is fairly small, less than root n or something like that, has about a 1 over root n fraction of all the edges of the hypercube. So you can write down a little combinatorial expression with sums of binomial coefficients and so on for exactly how many edges you slice. But basically, it's d root n. This is their conjecture. But unfortunately, we don't know if it's true or not even for d equals 2. OK?
For
what is known as the results of this talk, which I'm just about to get to, yeah. So yeah, there really wasn't much progress on this, as far as I could tell, for quite some time. You'd think, this is ridiculous, how hard can it be? But this picture has nothing to do with the talk. It's just kind of up there to illustrate that even relatively low degree polynomials can be kind of complicated objects, right? This is, you guys probably know this better than I do. This is the Calabre-Yau manifold or something like that. It's some fancy polynomial of degree 5. It's not necessarily so easy to reason in a geometric way about these things. Good, so what is known? I guess the main result of the talk is that we have a non-trivial upper bound on this average sensitivity, on how many edges a degree D polynomial surface can slice. So the theorem says if you have a degree D polynomial, the average sensitivity is going to be at most 2 to the D. If D is constant or something small, this is not a big deal, times n to some power which is less than 1 for any constant d, n to the 1 minus 1 over, say, 5d. The 5d, 8d, 4d plus 3, don't worry too much about that. Okay, but basically looks like this. We'll see where the 5d comes from. So there's an asterisk. Why is there an asterisk? The theorem, this is true as stated, so that's not what the asterisk is for. The asterisk is a couple of things. So in this work, we also give a totally different proof, which essentially gives us a weaker bound, except for a very small d. So using different techniques, you can show an upper bound of, I think, 2 times n to the 1 minus 1 over 2 to the d. So if d is like 2, this is n to the 3/4, right? It beats, I don't know, n to the 9/10 or whatever we're getting exactly up here. But for d larger than 4, I think you'd rather have this bound than this bound. Okay, so I'm going to focus on telling you about this one. That's one thing. Second thing is this is joint work with, I guess, Ilias Diakonakoulis, Prasad Raghavendra, and Li-Young Tan. And independently, Adam Clivens, Prahlad Harsha, and Raghu Meka proved essentially the exact same theorem using essentially the exact same techniques. So in a month or so, these works are going to be combined for the conference version. But I'll just, I'm going to focus just on our presentation because it's sort of clearer, at least in my mind. OK, I think that's the extent of the asterisks. So just to stop and look at this again, let's compare this bound with what we sort of, if you believe this Gotsman-Linial conjecture, right, then the right bound is d square root of n. That's quite a bit stronger, right? We're exponential in d, and obviously we're quite a bit weaker in n as well. But it's some kind of non-trivial bound, certainly for any constant d, even for slightly super constant d. And we'll see that you can get some interesting applications out of this bound. And for some of these applications, for one of the applications, having the conjectured bound would strengthen it quite a bit. For another application, it wouldn't really strengthen it that much. We'll see this in the application section. But for the next chunk of the talk, I want to give you some idea of how this is proved. Was there a question?
So do we know if this conjecture is also tight in the range d really large? For example, let's say d root n, can you cut almost all the edges of it?
Yeah, so if d is like root n, right, you can cut the middle root n layers of the cube, and that'll have 99% of the edges, yeah. I mean, it's certainly not, I misphrased their conjecture to say it's d root n in general. For d equals n to the 2/3 or something, they're not conjecturing that. They're conjecturing, yeah. OK, so that's where we're headed for the next chunk of the talk. I'll tell you a little bit about how this is proved, OK? OK, so we'll do an outline of the proof. There are kind of 2 stages that I'd like you to think about separately. The first stage is talking about a special sort of case, so-called regular polynomial threshold functions. Okay, so for the next little bit, we'll argue that regular polynomial threshold functions have pretty good average sensitivity. We can prove some kind of bound like this for them. And the 2 main ingredients there, it's not a complicated argument. We just sort of need 2 pieces of machinery, the invariance principle and concentration bounds on polynomials and Gaussian random variables. Okay, so we'll go through this. It's not too tough. And then I'll sketch how we have sort of a reduction that lets us convert general polynomial threshold functions, lets us apply the bounds we have in the regular case to arbitrary polynomial threshold functions. Okay? But first up, we'll talk about these regular PTFs. OK, so what is a regular PTF? I'll be talking about regular PTFs for a while. Whenever I say regular PTF, what I mean is the sign of a regular polynomial. OK? And what is a regular polynomial? A regular polynomial, intuitively, is a polynomial where the influence of each variable is just a small fraction of the total influence of all the variables on the polynomial. Okay, you can make it quantitative by saying a polynomial is tau regular if for each variable I, the influence of variable I on the polynomial is at most a tau fraction of the total influence. Okay? So it's some measure of having no variable with too much influence.
That generalizes from linear threshold functions of looking
Exactly, exactly. I was anticipating my next couple slides saying, in linear threshold functions, this would just be like some condition that no weight is too large for each guy. Yeah. I was trying to create a little mystery saying, hey, I didn't even tell you, right? What is the influence of a variable on a polynomial? Right? We had a definition of influence. It's the probability that flipping the bit flips the value of the function or changes the value of the function. But obviously, this is not the right definition for a polynomial, right? I mean, you don't really care about changing the value of the function for a polynomial. You want to look more at what's really going on. So for polynomials, you can think of the influence of a variable on the polynomial as essentially just the Fourier weight, right? So you have the Fourier representation of the polynomial. You have a bunch of coefficients, some of which are on monomials that include that variable, some of which are on monomials that don't include that variable, xi. The influence of the variable is just the Fourier weight, the sum of the squares of Fourier coefficients on all the monomials that actually do contain xi. Okay? So you've got your polynomial representation. I should mention clearly at least once that we'll always be thinking about multilinear polynomials, right? Because we're concerned with the Boolean cube as our domain, so there's no reason to have non-multilinear polynomials. So you give me a multilinear polynomial, right? I just look at those variables monomials that contain variable I, and I take the sum of the squares of those Fourier coefficients, and that's our notion of the influence of variable I on a polynomial. Russell, you look like you're about to say something.
Can you rephrase that in terms of like the expectation of the difference between the polynomial at x and the polynomial at x?
Yeah, that's coming right up in the next slide. Yeah, yeah. The expected value of the variance of the polynomial. Yeah. I'm a weird guy, so for me this is a natural notion. But yeah, that's the general notion of influence of a variable in a product probability space. Yeah. So again, if you're concrete-minded like me, here's a little example. So there's no doubt as to what this notion is, right? You have your polynomial, influence of variable 1. Well, every monomial contains variable 1, so it's the sum of the squares of those coefficients. Variable 2, variable 3, you get the idea, right? You just look for the monomials that have the coefficient, that have the variable, take the sum of squares. And like Russell said, you can define this, you can think about it for a minute and see that our earlier definition for Boolean functions, where it's just the probability of flipping the value of the polynomial, if your polynomial happens to actually be Boolean valued, and this definition, the sum of the squares of the Fourier coefficients containing that variable, they're both special cases of a more general definition that the influence of variable I on the polynomial is the expected value of the variance of the polynomial, right, where you just let it be a function of variable I, the expected value over all possible ways of fixing the other input bits. Okay, so if you like to think of it that way, that's what the influence is, the expected value of the variance of the function as a function of the ith coordinate. Okay? So now we know what the influence of a variable is on a polynomial, clearly, and we have, again, remind you of this definition, that a regular polynomial, a tau regular guy, is one where every variable has only a tau fraction of the total influence. Okay? Okay. Good. So why do we care about regular polynomials? Why should they be a special case that'll be easier to handle?
Think of it as a constant or
no. Tau's going to be a polynomial. It's going to be a polynomial in n. It's going to be close to n. It's going to be like n to the 0.9 or something. Yeah. 1 over n to the 0.9. Sorry. Yeah.
So it's better to compare it to the average influence sometimes.
Yeah. Yeah. I guess you could. Yeah. 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 Okay. Right. Okay. So regular polynomials. We're going to, we have some nice tools for regular polynomials. In particular, one thing we have going for us is the invariance principle. Right. We're going to think of the invariance principle as saying that if you have a regular low-degree polynomial, then viewing the polynomial, the output of the polynomial, when you feed it random binary inputs, that's some probability distribution. That distribution is close, right? Its CDF is close to the corresponding probability distribution that we'd get if we just fed in Gaussian inputs. Okay, so the polynomial is the invariance principle. It's invariant whether you sort of think of the independent inputs as bits or Gaussians. Right, so I don't think I'm going to use this notation much, but what I just mean here is, again, the CDF, on this side is, never more than tau to whatever, 1 over 5d, far from the value of the CDF on this side of this guy. Okay, so that's going to mean we can reason about polynomial over Gaussian random variables, and we have some more tools there than we have in the Boolean case. In particular, we have concentration bounds. Okay, we have tail bounds, for degree D polynomials over Boolean inputs as well. That's not a big deal. But we also have anti-concentration bounds. There are these nice results which tell us you give me a polynomial in Gaussian random variables, it can't put too much weight on any small interval, any small range of outputs. And that's going to be useful for us. OK, so let's kind of see how that's going to be useful for us. Let's think about bounding the influence of just a single variable in a regular polynomial threshold function. OK, so P is a regular polynomial. We think of some fixed input x, right? F of x, sine of P is our polynomial threshold function. And we just want to know, for this particular input x, is x1 kind of an influential variable? Is the PTF sensitive, for this input x to the first coordinate? So, we sort of know exactly what that means, right? Our polynomial, we can factor out x1. It's x1 times, some coefficient plus some other coefficient. And, here's P of x. It sits somewhere on the number line. When we flip the first bit, right, well, we get one of these two values for P with the first bit flipped, depending on whether I guess x1 was +1 or -1. In the original input x, we either go one way, we go down by 2 times the magnitude of the coefficient of x1, or we go up by that amount. OK? So one thing you can see pretty clearly is that if the coefficient of x1 in the polynomial, the value of this coefficient on that particular input x is small compared to the actual magnitude of the polynomial, then certainly x1 is not influential, right? Whether it flips this way or that way, it's not going to make you cross 0 and change sign. OK?
Sorry, what's this figure again? Oh, now it's done.
So P of x, it's like you fixed some input x, you're thinking about x, and when you flip the first bit, it changes the value of P of x by this quantity, 2 times the magnitude of whatever the coefficient of P of x is. We factored out x1 in P of x. We expressed it this way. And we're just observing that flipping the first bit changes the value of P of x by, you had been like adding this coefficient, and now you're subtracting it. It changes it by twice that. So if the magnitude of A is small, I think my battery's dying here, but if the magnitude of A is small in this input compared to the actual value of the polynomial, then it's not sensitive to x1, right? Flipping x1 won't change which side of 0 you're on. OK. OK, so this is just the same picture we just saw, right? But this tells us one way we can bound the influence of variable 1 on f is if we can think of some value, some threshold, I'm calling it alpha here, and if we can show, hey, with high probability, you get 2 things happening. With high probability, this kind of displacement when you flip the first bit, probability over a random x, right? If we can say with high probability, the amount you change, the amount the value of the polynomial changes by when you flip that first bit is smaller than alpha, and with high probability, the original value of the polynomial is larger than alpha, then right, that you just take the union bound, you have high probability for a random x that flipping the first bit doesn't change the value of the sign of the polynomial. Doesn't change the value of the PTF, and so you have low influence for the first coordinate. It's a simple argument, right? There's nothing fancy going on here. So, right, we'd like it to be the case that we can actually, make both these statements. With high probability, the polynomial's value, the polynomial A, has small magnitude for a random input, and with high probability, this guy is not too small, right? So we need concentration for the first statement, and we need anti-concentration for the second statement. We need it to be the case that there are not too many x's that cause us to lie in this small range around 0. OK, and that's where regularity comes in. It lets us get the anti-concentration. So just to go through it in a tiny bit more detail, right? For the first statement, we want to say, look, with high probability over a random x, this polynomial a, right, the coefficient when we factor out x1, takes a small value. And it's easy to analyze that. We sort of know its variance, right? It's just, again, the sum of squares. It's the influence of variable 1 in the original function, right? So we're in the regular case. We know that this is small. That's kind of what we assume to get into this case. And so what do we need to do? We just need to apply tail bounds on degree d polynomials. It's not likely to take a value that's much larger than the variance. Right, so like a Chernoff bound for degree d polynomials instead of a linear form. Regular polynomial is one in which each variable has small influence compared to the total influence.
Oh, OK.
Yeah.
All right.
So it kind of tells us that like the sum of the squared coefficients in A, for instance, is small. It's at most a tau fraction. Yeah.
So for what value of tau? So regular.
I haven't set tau for you yet. I'm just kind of trying to keep it like large, small. Think of tau as something small. Yeah. Okay. And for the other direction, right, we need to say, for the other part, we need to say, hey, it's unlikely that the overall polynomial takes a small value, right? So there is this alpha that we can choose, which is sort of, larger than this guy and smaller than this guy with high probability, right? So that's just, we need a statement which says this random variable p of x, if we feed it, uniform bits as the input, has good anti-concentration. It's not concentrated around the origin. It's not likely to take a small value. And we can do this by combining anti-concentration, by combining the invariance principle with these, I guess it's this theorem of Carberry and Wright, although I think there are versions of this that go further back than that. I think that 91 also should be a 2001. Yeah, so the invariance principle lets us say, look, you plug in bits to your polynomial. Since it's a regular polynomial, the distribution of where it lands will be similar to the distribution of where it landed if you plugged in Gaussians for the polynomial. And then this theorem of Carberry and Wright says, look, you plug in Gaussians to your polynomial, it's unlikely that it takes a very small value, right? That distribution can't have a lot of weight right around the origin. Does it make sense? I'm not obviously giving you the quantitative details of how it comes out, but this is the idea. OK. So that's a sketch of how we could bound the influence of a single variable in a regular polynomial. And in the regular case, we're not going to do anything fancy to bound the total influence. We're just going to say, well, every variable contributes at most this much. So n times that bound is a bound on the total influence. So this is all we do in the regular case, right? And what we end up being able to say is that if you're a degree d tau regular polynomial, then the average sensitivity is bounded like this. It's linear in d. We get this n is just from the union bound of applying the simple argument to each of the n variables. And if you work out the details of the concentration and anti-concentration bounds, you get tau to this power, 1 minus 1 over 4d plus 1. And that's from the invariance principle, essentially.
Where is the d?
This d comes from the concentration bound for degree d polynomials and Gaussian random variables, this Carberry-Wright theorem. Yeah. And I think it's...
But it's not exponential in d.
No, it's linear in d. I think you actually need that d, but don't quote me on that. Yeah. Yeah. OK. Amir, yeah.
You bound the average sensitivity by something, and then you bound this something by this number.
So I bound the influence of a single variable by this expression without the n. Yeah.
There is this event that A is small and P is large.
That's like for a single variable, yeah.
So
Yeah.
you find the probability of this event, and then you take like union bound.
Union bound, yeah.
So is the probability of this event this magnitude? So you expect the average sensitivity to be square root of it?
Yes, I think this is the lossy part of the argument. Right, we took a uniform bound. We said, look, I'm just picking some threshold. It doesn't depend on the structure of the polynomial or really anything. It's just, you give me tau, and I'm like, all right, I'm going to pick, this alpha from a few slides back, this cutoff. I think it's like tau to the 1/4 or something like that. And, we say, well, it's unlikely that A is larger than this, and it's unlikely that P is smaller than this, so we're in business, right? You could imagine that with more blood, sweat, and tears, or more ingenuity, you could have maybe a bound which depends in some refined way on the structure of the polynomial. And you could get, yeah, this is, I think, the lossy part of the argument.
So, and the probability of, so then this new number is, so this is an exact estimate of this new number?
This is the best bound we can give you on this new number. I can't say that I know that it's the best that this new number is, although I think I would be surprised. I think you'd need new tools to do better than this. Yeah, yeah. Okay. Okay. So that wraps up what I wanted to say for the regular case, which is kind of the easy case. I think more of the interesting part is in the reduction from general polynomial threshold functions or non-regular polynomial threshold functions to the regular case. Okay. So some ingredients that'll come up here. We're going to use random restrictions, but in kind of a careful way where we restrict the influential variables, not just randomly chosen variables, but the high influence variables. We'll need this notion of the critical index. I guess we use hypercontractive bounds, and there's kind of an easy recurrence which comes into the picture. So I'll at least show you the recurrence and talk a little bit about some of the other stuff. Okay, so irregular PTFs or general PTFs. The one-sentence explanation of how we deal with these guys is we show that a fairly significant number of restrictions, a fairly significant fraction of restrictions that fix the high influence variables cause the polynomial to collapse down and become a regular polynomial. Okay, and that's in business because it kind of gives us a toehold where we can use the bound for the regular guys. So we're going to prove, but we'll talk a little bit about this kind of new structure theorem for polynomial threshold functions, or maybe I should just say for polynomials. So let's think of tau now, some inverse polynomial. Tau is 1 over n to the 0.1 or something like that. The structure result says that if you give me a degree d polynomial threshold function, okay, there's a small set of variables, something like 1 over tau or d over tau, with this extra log n factor, but don't worry about it too much. So there's a pretty small set of variables which has the property that a lot of restrictions, 1 over 2 to the d fraction of restrictions, and that's a lot, right? D is like, 4 or something. A lot of restrictions have the property that when you apply that restriction to that set of variables, that small set of variables, and again, those are like the high influence variables in the polynomial, you'll get a pretty regular polynomial out. Okay? So it says if you look at just the high influence variables and you do a random restriction fixing those guys to +1 - 1, a decent fraction of the time, the polynomial you get out is a regular polynomial. There's a little twist here. We'll see what the little twist is, but just take this for the moment. Yeah, Russell already sees the twist. Damn you, Russell.
So it's a small constant fraction.
Yeah.
So what you're going to have to do is say, we do it once, and either we get lucky and it's regular, or it's not, and then we do it again.
That's the recursive.
Chance of
Yeah, exactly. That's the little recursive thing. That's not the twist I was talking about. So forget I said anything. Forget I said anything about the twist, right? But yeah, exactly. That's how we'll sort of use this over and over. Yeah. Good. Okay. So let's see what's going on. So let's pretend we have this statement. I'll talk about getting that statement in a minute. Right? We know that for regular polynomials, we're good. We can get some kind of non-trivial bound on average sensitivity. If you're not regular, this is just a restatement of that structure thing from the last slide. If you're not regular, then there's a set of not too many variables. Think of this as like the head variables. They're like the heavy variables, whatever acronym you like that starts with H. Right? These are the high influence variables. Not too many variables with the property that a lot of restrictions to them make your polynomial pretty regular. Right? And then just like Russell said, what are you going to do? Well, you can bound the overall average sensitivity of the original PTF by, we're going to think of it again as a sum of the influences of all the variables. So you've got these heavy variables or head variables, and you've got the other variables. Right? For these guys, the heavy variables, the head variables, we'll just do a trivial thing and say there's h of them. So each one certainly has influence at most 1. So we trivially go from the first sum down to this expression. Right? This is the number of those guys. For the second guy, right, what do we have to do? These are the variables we didn't restrict. Right? Well, the total influence of those variables is just going to be the average overall restrictions of the total influence of the restricted function. Right? If you think of it as like slicing edges in the cube, it's easy to see that. Right? And just to repeat what I said, we do a trivial bound to say each of these restricted variables contributed at most 1 to the influence of the original guy. For the unrestricted variables, we know that a decent fraction of the restrictions give us that the polynomial f sub rho is regular. Sorry, the function f sub rho is the sign of a regular polynomial. Right? So we can, for a 1 over 2 to the d fraction of the restrictions, like Russell said, we have some kind of non-trivial bound on the influence. And for the other restrictions where we didn't get lucky, yeah, we just try again. We say, well, this restricted guy is himself some degree d polynomial threshold function, so I'll rerun the argument. Right? So it's kind of clear, hopefully, where this is going. Right? You get this little recurrence, which gives you an upper bound. I guess I'm writing as of s of dn here to mean the worst possible average sensitivity of any degree d PTF over n variables. Okay? So you can just recursively kind of bound this by saying it's what you paid for these variables in the head plus what you paid for the restrictions where it came out regular, and at least some of the time, right? So you're saving a little something here over a multiple of 1. You just recursively run the argument. So, you choose tau in the right way. You look at this recurrence, and you get the result out. Right? You get the 2 to the d because it's like a 1 over 2 to the d fraction of the time that you save something. You can kind of see where it comes from, I think. So that's the high-level structure, given this. That's the high-level outline of the proof, given this kind of structure theorem about PTFs, or about restrictions, the way restrictions affect polynomials. Okay. Good. So let's sketch in the next couple slides the idea behind this sort of structure theorem. And again, what this theorem says is you give me any degree d polynomial. Think of a regularity parameter, which is like some inverse polynomial, 1 over n to the point 1 or something. There are a lot of restrictions which fix not too many variables, right? Those first high influence variables of the polynomial, fixing them in all possible ways. A lot of those restrictions make the resulting polynomial be close to regular. Be regular. Sorry, what I should really say, and you'll see why I have to say this, is make the resulting function be a regular PTF. Is Russell going to call me on it now? He's not going to call me on it yet.
No, I'm missing an entire.
Man, I'm dodging a lot of bullets here. This is great. OK, so let's see how it goes. So it's just going to be a case analysis based on this notion of the critical index. The critical index is something we used to talk about for linear threshold functions. In this work, we generalize it in, I think, a natural way to polynomials. So let's pretend we've ordered the variables x1 through xn in decreasing order of influence. So the most influential variable, the second most influential variable, and so on and so forth. And I'm drawing for you like a histogram of the influence of variable 1, influence of variable 2, so on and so forth. The critical index is a way to make a statement about this histogram, sort of talking about how quickly it tails off. Okay, the exact definition is the tau critical index of the polynomial is the first point in this histogram, the first I, such that the influence from that point on, the total influence of these guys, I plus 1 through n, is at most, the total influence of the biggest remaining guy, the I plus first guy, is at most a tau fraction of the total remaining critical index. You can think of it as like the first point at which this histogram becomes like the histogram of a regular polynomial. Right? For a regular polynomial, you know, from the very first variable, the most influential guy already doesn't have a tau fraction of the total. And here it's like you look at the whole histogram and you're like, this guy, he has too much influence. It's more than a tau fraction of the total. Forget about him, right? Cross him out. Just look at the remaining guys. Does this guy have a tau fraction of what's left? No? Keep going and so on. Eventually you reach a point where this guy is the first guy who has, you know, less than a tau fraction of what's left.
Is it obvious that the remainder is tau regular? Because you only look at the suffix.
If you think of tau regularity as a property just of like a histogram, yeah, then by definition it is. Yeah, yeah, yeah. Yeah, we sorted the variables. OK, good. So I won't go through the statement again, but the case analysis intuitively is that there are two cases. The tau critical index is either small, less than something, or it's large. OK? So let's think about the small critical index case first. Intuitively, that's a polynomial where the histogram looks like this. You have a couple of high influence variables, and then the histogram is like tau regular. There's nobody with too much influence compared to that sum. So like I think Avi was maybe saying a second ago, when you actually, you know, this actually comes from some polynomial, and when you do a restriction, kind of funny things can happen. Right? If the polynomial is this, you know, this little example where the influence of variable 3 is 29, for this particular polynomial, because 5 squared plus 2 squared. When you do a restriction, when you restrict the first variable, it's not so clear what happens. If you set x2, or you set the second variable, let's say, to 1, now the influence of the third variable is 9, but if you set it a different way, the influence of the third variable is 49. Right? So it's not like, because you have terms, it's not a linear threshold function, right? You have sort of crosstalk between different monomials, things collapse onto each other. So its influences of later variables can change when you do restrictions. Right? They can go up, they can go down. You have to deal with this. But if you notice from this little example, the average of these two possible values for the influence of the third variable, 9 and 49, it does come back home to where it should be. The average is 29, is what the influence was in the original function. Okay, and this is not a coincidence, right? This kind of thing has to happen in general. It's very easy to show that if you take a random restriction over some bunch of variables, the expected value of the influence of some later variable that you didn't restrict is going to be just whatever the original influence of that variable was on the polynomial. Okay? Moreover, if you think about it, right, you can kind of see that the value of the influence of variable L on this, in this side, for a given row, the influence of variable L can be expressed as a low-degree polynomial in the variables row 1 through row whatever, the guys that you restricted, right? Because influence is like a sum of squared coefficients and so on. So you can make statements, you can make high probability type statements about what happens when you do a random restriction. Okay, the actual value of the influence for a given restriction is some low-degree polynomial, so we can talk about how it behaves. And you can show that with some non-negligible probability, it doesn't skyrocket. No guy gets too large. Okay, so I'm not kind of going through the details, but hopefully there's some intuition here that you can show there's at least some reasonable chance that when you do a random restriction, things may change, but there's a fair number of outcomes where they don't change too much and it stays pretty regular.
So this is also using invariance here?
This is not using invariance. This is just using, I guess, tail bounds for degree 2D concentration. Yeah, concentration of for polynomials. Yeah, yeah.
And in the
Kim
last,
Wu or something like this?
No, just sort of what I think of as like degree D Chernoff bounds. Right? You give me a degree D polynomial in bits, it's unlikely to take a value much larger than you'd expect. Yeah, not fancy. Just the tail bounds that come from like, the 2 or 3 line proof from hypercontractivity. Yeah.
So how many variables do you restrict here in this thing?
Good question. So this was this is like the small critical index case. So we restrict up to the critical index, not too many variables. But notice the probability bound doesn't depend on how many variables we restrict. It just depends on D. Yeah. OK. So that's the small critical index case, right? You have some decent chance that it doesn't get too irregular, and we're in business still. The large critical index case, how does it go here? Well, the critical index is large. You have to go way far out until you reach a point where the remaining histogram of influences is regular. In this case, right, we think like, what does this definition of the critical index tell us? Well, by definition, before the critical index, every time you're before the critical index, this bar is like a tau fraction of the total height of all the remaining bars, right? And that happens again here, and it happens again here. It's not hard to show that, it's like a 2-line argument that, since we sort of define the critical index this way, sorry, did I miss? I was trying to make a point. Yeah, the point I want to make is, think of this guy eats up a tau fraction of the total sort of remaining influence. And then this guy eats up another tau fraction of the 1 minus tau surviving remaining influence and so on. So the total sort of remaining influence is going down exponentially, like powers of 1 minus tau as you're going through this thing. So if the critical index is large, there's very little influence left out here. Okay, that polynomial.
Not just there, even from there, right?
Even from here, yeah. That's right. Once you're even past this point, there's just not a lot of oomph left. It's sort of like the
Exponentially small in D.
Exponentially small in this critical index. It's like 1 minus tau to this point that you went out to, and so yeah. So it's like 1 over n to the d or something. It's very, very, very small. Yeah, that's a good way to think of it. 1 over n to the d. The polynomial only has n to the d coefficients, so it's really, really small. So what does this actually show? This is the asterisk I kept on worrying that Russell was going to call me on. Whoops, I think I went ahead one too far. Yeah. What you can show here is that with some decent probability, a random restriction makes the polynomial threshold function into a constant function. Okay? Basically, the coefficients, so you do the restriction out to this point. You don't restrict past here, right? The monomials which survive this restriction have such little sort of sum of squared coefficients, such little influence remaining in total, that with high probability, they're just completely incapable, even if you set the remaining variables in exactly the right way, they're completely incapable of bringing the value of the polynomial to the other side of 0 from where it started, by virtue of having set these variables. Okay? So this is the asterisk, right? This polynomial piece of rho is not necessarily regular, right? I mean, you can write down kind of a trivial example where, I apologize to the cameraman if this is trouble. If the original polynomial is something like sum of xi over 2 to the I, right, then I don't care what restriction you do, it's not going to become regular, right? Whatever the first unrestricted variable is, it has a lot of mass compared to everything else, right? But think about like doing a random restriction to this guy. It's very likely if you're setting the first bunch of variables that you don't come out, you need all the bits to come out in exactly the right way to make sign of this be a non-constant function, right? If the first bit comes out as +1 and the second bit comes out as +1, you're screwed, right? You can't, no matter how you set the remaining bits, it's not going to go back to 0. So that's what's going on here, right? I'm not saying the polynomial, this was kind of the asterisk I was talking about. P sub rho does not necessarily become regular, but the PTF sine of P sub rho becomes constant. And that's a low influence function, right? That's a, you can think of that as just the sine of some other regular PTF if you want, or sine of some other regular polynomial. It just, it has 0 influence, obviously. So this is a good case. So just to recap the structure theorem, right? It basically says there's always a set of not too many variables, either going up to the critical index if it's low, or going up to this point if the critical index is high, such that a decent fraction of the restrictions to those guys give you a regular PTF. And they kind of do it in 2 ways. If the critical index is low, restrict up to the critical index, and with some probability you actually get a regular polynomial out. If the critical index is high, just restrict up to this point, and with some pretty good probability, it just becomes constant, the PTF. OK? So the actual statement is a little stronger than this, but whatever. So that's it. That's the sketch of the structural result. We talked about how the structural result with the little recursive argument gives you, together in tandem with the argument for the regular case, the influence bound. So that's the main result. I'll keep going for a little bit and talk about some of the applications. OK. I don't know how hungry people get at like 12:15, 12:20, or when.
Plan for 12:15, and if we
OK.
need to continue.
OK.
Willing.
We'll see. We'll see how hungry I am. Yeah. OK. So let me talk at least a little bit about applications. This part will be a little lighter. So the first application is to getting some new learning results for richer classes of circuits. So just to remind you, there was this work of Linial, Mansour, and Nissan, who gave a quasi-polynomial time algorithm for learning AC0 circuits. OK, so constant depth and or not. They could learn them in quasi-polynomial time. And it's an argument based on Fourier concentration. They show that these circuits don't have a lot of Fourier weight above polylog many levels. A while after that, I guess 9 years after that, we, with Adam Klivans and Jeff Jackson, gave a quasi-polynomial time algorithm for a slightly richer class, right? So majority of AC0. You can put a majority gate at the root, and we can still learn these guys in quasi-polynomial time. It was sort of a hybrid argument where we used, not a hybrid argument, sorry, it was just a hybrid of the Fourier techniques from these guys and boosting some machinery from computational learning theory. And to get this result, it really depended crucially on the fact that it's a low-weight majority on top. OK, because that's just key to getting the boosting to work.
Also slightly bigger. It contains ACC.
It's nice of you to say that, Avi. Yeah. OK, so yeah, it was bigger.
Majority of AC0, yeah.
Majority of even
Quasi-polynomial.
verities and ends is
Quasi-polynomial.
Quasi-polynomial size is OK. You could also have polylog many majorities. A result of Beagle says if there are polylog many majorities in the circuit, yeah. So a question that we asked back then was, can we do a little bit better? Can we learn threshold of AC0? So an arbitrary LTF on top, a high weight threshold function. This work in 2002, the paper was called Learnability Beyond AC0, and I tried to convince Pariksha to call this one Learnability Beyond AC0, but he wasn't up for it, so it has some other less memorable title. But it turns out we can go beyond this, and we can at least start to answer this question about learning threshold of AC0. So the main result is you give me a threshold of AC0, and we can learn it to, say, 99% accuracy. And it's not quasi-polynomial time, but it's some sub-exponential time bound, 2 to the log n to the 2/3. OK? So the average sensitivity bound for low-degree PTFs is the key ingredient, the key sort of new thing we needed to get this. If the Gotsman-Linial conjecture were true, if we had a stronger bound, then we would get quasi-polynomial time. OK? So we believe that we know the algorithm which works in quasi-polynomial time, but we don't have a proof because we don't know the Gotsman-Linial conjecture.
So you are going to say what the algorithm is?
The algorithm is the exact same as the original LMN algorithm. There's no boosting. It's just Fourier concentration. Yeah, that's coming up on this slide. So we just prove Fourier concentration, that these functions have Fourier concentration. I'm hiding something from you. The concentration is worse as a function of epsilon. So LMN, I guess, got something like their running time bound was something like if m is the circuit size, the dependence on epsilon was log to the d of 1 over epsilon, because they only had to go up to like layer, polylog m over epsilon to get all but epsilon of the Fourier weight. Even for just the majority function, if your circuit is just the majority function, you have to go up to layer epsilon squared to get all but epsilon of the Fourier weight. So if you think of this as like a constant epsilon statement, that's how this is possible. Yeah, and it's, you're not going to get a better result based on Fourier concentration because of something like this. So just half a slide of a sketch of how it's done. So LMN, what do? They have random restriction arguments which let them relate Fourier concentration of the original AC0 circuit to Fourier concentration of the shallow decision trees that you get out of hitting the AC0 circuit with a random restriction. If there's one class of functions where it's easy to talk about Fourier concentration, it's shallow decision trees, because there's just nothing up there, right? It's a low degree polynomial at a 0 Fourier weight at coefficients larger than the depth of the tree. So now we're going to use the same kind of argument. We're going to talk about random restrictions, right? We hit our threshold of AC0 with a random restriction. Well, there's a threshold gate on top, so it's not going to collapse down to a shallow decision tree, but it will collapse down to a low degree PTF. Basically, it's a threshold of shallow decision trees, which is a low degree PTF. You take sine of some weighted linear combination of these decision trees. So what do we need to make it work? Well, we need that these low degree PTFs have Fourier concentration. And I haven't told you yet that they have Fourier concentration. I've told you they have average sensitivity. It turns out they also do have good Fourier concentration. And the way that we know how to establish that is by showing that low degree PTFs have good noise sensitivity. So this is my segue into the second application. Is there a question first, or?
So one thing that was bothering me
Yeah.
is, and maybe I also see the loophole, is that if you use most random restriction methods,
Mm-hmm.
you start with an AC0, the depth is going to be, the depth of the decision tree is going to be some polylog.
Yeah.
That depends
Yeah.
on the depth of the AC0.
Yeah.
And then when you plug that as your degree and you have another exponential,
Mm-hmm.
in terms of average sensitivity, it's not going to give you anything.
Yeah.
But then, so maybe there's some, when you're dealing with actual AC0 rather than
Threshold of AC0?
well, actual AC0 rather than like quasi-polynomial size.
Yes.
Then
Yes.
maybe you can get the depth to be constant.
You can see that with this bound, if I didn't, so the n here, this is a little sloppy, right? The n here is shorthand for the poly n that is the size of the circuit. If this circuit that I started with was not just a threshold on top, but it was of size, n to the log n to the 100, that this would be trivial. Yeah, this would give nothing. So it's for polynomial size threshold of AC0.
You have to be very careful with the random restriction.
We're very careful. Yeah, it's a strong random restriction. It fixes more variables than.
But you still, the outcome is that the decision trees have depth polylog.
Polylog, yeah. So we have to hit it.
The degree of the polynomial threshold functions that you get are.
With the usual arguments, you're right. We hit it with a stronger random restriction, so it collapses to a much shallower decision tree. And then we can say, okay, it's
Stronger random restriction. What do you use?
smaller row parameter. We use, we just.
You use like power of n. You don't.
Yeah,
okay,
we
so
just
you
hit it.
can get a constant.
We just hit it harder. Yeah,
Okay.
yeah. Okay. Good. I'm glad I didn't put in the details. You guys filled in the details for me, so that's good. Okay, yeah. So segueing, right? It comes down to Fourier concentration. We get Fourier concentration of these low degree PTFs from having noise sensitivity of these guys. So that takes me to the second application, which I'll just briefly mention. So I've been talking about average sensitivity. That's like the average sensitivity measures like the probability that the function's value changes when you flip one bit. You could think of noise sensitivity of a function as some kind of measure of the probability the function's value changes when you flip several bits. So more precisely, the noise sensitivity of a function at noise rate epsilon means you pick a random input x, then independently for each of the n coordinates, you flip it with probability epsilon. Okay, that's how you generate your y. And the noise sensitivity of f at noise rate epsilon is just the probability that f of x changes values when you perturb x to get y. Okay? So it's got all kinds of applications, but it's getting toward lunchtime. There are relations between noise sensitivity and average sensitivity. Again, it's getting toward lunchtime, but Okay, well this is not that interesting. Just as a generic fact, if you have a bound on noise sensitivity, that always gives you a bound on average sensitivity. Okay, you can think of average sensitivity as like a special case of noise sensitivity. at noise rate 1 over n. Intuitively, if you flip each bit independently with probability 1 over n, it's like flipping one bit. Okay? So we'd like to go in the other direction, and it turns out you can go in the other direction for polynomial threshold functions. We're able to leverage the average sensitivity bound for PTFs to get a noise sensitivity bound. So I'll tell you the statement of this. The statement is, OK, suppose you've got some upper bound on average sensitivity for degree d PTFs in n variables, OK? That automatically gives you an upper bound on noise sensitivity. You just sort of pretend that the PTF is on 1 over epsilon many variables, look at whatever your average sensitivity bound was, multiply it by epsilon, and that gives you a bound on noise sensitivity. OK? So I don't want to go into the proof. If you've seen Perez's proof, this nice proof of noise sensitivity for linear threshold functions, right? It's this clever idea where you sort of throw variables independently into like 1 over epsilon many buckets, right? And then you're like, OK, now I'm going to pick one of the buckets and flip the entire bucket, right? So it's like flipping one entire bucket is kind of like flipping one variable, right? Instead of like, the 1 over epsilon buckets are like 1 over epsilon variables. Same thing essentially is what's going on here, OK?
I mean, isn't that literally what's going on? So you're just
Yeah.
these buckets, we're going to just identify those variables.
Yeah.
And that creates a new.
In this case, it creates a new polynomial of the same degree. Exactly. Yeah. 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 That's it. It's a simple argument.